speaker today is Maciej Bilicki. I don't have to present him. He is with our institute since a couple of years already, doing cosmology. And the topic is, are we somehow specially located in the universe? Or at least this is how I understand the title, right? What's wrong with our position? Okay. We'll hear the answer soon. Welcome.
Yes, thank you, Bożena. Yes, it's been 7 years.
Yeah.
That I'm here. I started 1st February 2019, so quite a bit already. So I decided to present this after the director spotted that I had I was a co-author on a PRL paper, and this is of course 200 points for our ministry. So this is very valued by our institute. The ministry doesn't care if you're first author, 7th or 700 or whatever, as long as it's a bit absurd, but doesn't matter. Yes, I was on a paper, and around this paper I built a whole talk. I already gave it in Krakow. Because I think it's an interesting result, which is based on many previous attempts on this. So this is about measuring our motion from radio data, and there is a puzzle that is there, and some people claim it's really severe, several sigma, and that it's as severe as Hubble constant tension, but maybe it's a bit more obscure why this is and what is causing it. Okay, so I will start with really basics, because some of you are not cosmologists, but I also wanted to put it in the perspective of why this measurement is puzzling and why it's also relevant. So I think it's worth starting with really these basics here that are in the, let's say, first pages of any textbooks usually. That basic assumption of standard cosmology, which is with us for 100 years, and it's not lambda CDM, it's generally assumption of the standard cosmology, is that there is, first of all, Copernican principle that we are not special, and secondly, there is the cosmological principle that no place in the universe is special.
Question: did Copernic ever write something like that, or that's just a name? You know,
I don't think he wrote it. He only said that the center of the, well, it's not exactly that, but the Earth should not be in the center, that it's rather the sun. I think he was even using
saying we are not the center. It's not the same as we are not special, right? Because the sun would have to be special.
Generalization.
So I'm trying to clarify what is meant by that. This is these are not mathematical terms, special, of course, yes, but what is meant here that we as observers are not central in whatever way you think of it, or privileged, so that we are not in some position which is privileged over other positions in the universe. It doesn't mean that we are in a totally random position. If we were in a totally random place in the universe, we would be inside a big void, because this is the most of the universe in terms of volume. But mathematically, these assumptions mean that there is universal homogeneity and isotropy. Basically, you have to have this, and just to remind you, isotropy is that every direction you look is the same, but mathematically it means that there is rotational invariance to your measurements, let's say. So, and homogeneity means that, again, it looks the same from every place, which is translational invariance. And here are two examples of isotropic and homogeneous distributions, which are not the other. But as is very nicely shown in John Peacock's textbook, I think it's a nice, very short, Gedanken experiment, that isotropy around two random points implies global homogeneity. You can show that if you have isotropy around one random and the other random point, then you have to have global homogeneity. And of course, these things are meant in a statistical sense. And again, in quotation marks, this would be sufficiently large scales, because of course we are not, our universe is not exactly homogeneous and isotropic, because we wouldn't be here. because we need to have over densities, for instance, to form galaxies or planets. And sufficiently large scales is a vague term. It's not really, there is no really definition what it means, but typically we assume that scales of, let's say, 100 megaparsecs should be already these scales. In other words, there are structures in the universe which are large and which are not homogeneous, not isotropic, and they are both predicted by theory and also by cosmological simulations. But if you go, and these larger structures are basically superclusters or voids, and they can be up to a few dozen megaparsecs. Beyond that, you assume that on average, these assumptions are met. So one historical remark, in my opinion, is worth doing here, that not, as some people may think, these assumptions are not they are not just within the current standard Lambda model. They were there already, kind of obvious for the pioneers, including Einstein himself, who not only wanted to have homogeneous isotropic universe, but also static, because not only he did not know anything about observations, the observations were not there in his times. It was not even known there are other galaxies, yes? But also other pioneers like de Sitter, Friedman. If you look at Friedman's original papers, it's just obvious. He just assumes homogeneous isotropy and then works out from Einstein equations his equations. Lemaitre the same. Of course, then Lemaitre went further and he did construct with others as well non-homogeneous like Lemaitre-Tolman-Bondi models, etc. There are also anisotropic models like Bianchi, etc. But it's worth remembering that even before any observations were really made, this was the assumptions, and it stays. But back then it was rather philosophical. Now, people try to test this because these are assumptions. If they are not met, our model will not be correct, because the assumptions give you Friedman equations and many other things. The problem is that, as the whole cosmology has this problem, that testing such kind of assumptions is very difficult, because observationally you are just one observer. Even if we manage to send a probe, let's say outside of our galaxy, that would be not enough, because the universe would look very much the same from, I don't know, a few 100 kiloparsecs away. You would have to be really very, very far away, dozens of megaparsecs, to really try to test these assumptions if they're met somewhere else. So this is not possible. What we know also is that in the early universe, the universe was very homogeneous, in a sense that fluctuations that we see in cosmic microwave background, which were generated around 400,000 years after the Big Bang, are like 10 to the -5 amplitude, except for the dipole, which will be focus of this talk. In the so-called late universe, so last few billion years, there are many approaches. It will be a separate talk how people try to test homogeneous isotropy in data. But most of these tests, well, one of the main outcomes of this test is that there is no evidence that the universe will be fractal, in a sense, as there were some people postulating, it's now not really anymore, but that you can still have structures larger and larger, like in a fractal sense. There is no evidence for that. So this kind of homogeneity scale is observed at some 100 megaparsecs. So whatever metrics you come up, people measure different things like correlations or some other things. They converge to homogeneity about 100 megaparsecs, which is quite large, I would say, because structures are much smaller than that. But because of gravitational instability, you do have sufficient large inhomogeneities that, well, they are not large in terms of amplitude, but they are there. So these scales are roughly this homogeneous scale. Isotropy is more difficult to test, because then you have to look in different directions, and you would ideally want to have some catalog of data set of full sky. Even if you do it from your viewpoint, if you just look at one half of the sky, you don't really know what's on the other. So it's very hard. And observationally, this is difficult, because to have in whatever wavelength you measure the sky, to do it over the whole celestial sphere, you have to either put two instruments on the Earth, so on two hemispheres, or you have to send something to space. You can imagine that both are challenging, especially in the first option. You would have to have really identical instruments if you are after some things that I will be talking about. And even then, there were such instruments, for instance, Tumas experiment, which had two identical telescopes, but the conditions then were different in Arizona than in Chile. So even then, despite the same mirrors, the same instruments, measurements are not exactly also matching because you have different conditions. So, and then, you know, in other wavelengths, often you have to send to space anyway, like X-rays or gamma rays, etc. And then it's costly, but it's, yes, there are methods, of course, to test also from not full sky. I will mention some of them, but this is, of course, under some assumptions. Now, going back to some basics again. So if you take any textbook and you can work it out on your own, you start from Einstein equations. You use well, okay, so before you go to Einstein equations, universal, so the global homogeneous isotropy lead you to a metric which can be presented in this way, Robertson-Walker metric. Of course, these are some specific coordinates. You can choose whatever you want, but typically that's how we do it. We have a time coordinate, we have some radial coordinate, and we have two angular coordinates because astronomers like it. Radial direction and angular, that's what we like. Of course, you can do it in Cartesian as well if you want. The funny thing that I always was from the very early days when I started studying cosmology, if you start learning GR and you are told that coordinates there should not be like separate time and space, and then you learn that in cosmology actually you do have separate time and space. This is very weird phenomenon that is kind of against what you would think about relativity. And some people have a problem with this. There are some models, like I think it's called timescape cosmology, and when there is, it's like about that actually there is no standard cosmic time, but in standard cosmology there is what we call sometimes cosmic time. So you separate time and space dependence already in the metric. A is called scale factor, and we also have kind of notion of co-moving coordinates. So if you take out the scale factor, the co-moving coordinates are independent of the expansion or contraction of the universe. Now, about contraction or expansion, of course, if you plug in the Robertson-Walker metric into the Einstein equation to go for Christoffel symbols, it's like a standard exercise in GR or cosmology classes. You arrive at the Friedmann equations. They can be presented this way, where you have all the things that we worry about in cosmology. So the density of something, typically matter, some pressure of, again, maybe radiation. Lambda is the cosmological constant. You can, of course, make it more complicated if you add some other fluids, but the standard ones which have these main fluids are like this. And the main result, if you try to solve them, is that universe cannot be really static. So the model that Einstein postulated is one of the solutions, but it's a very unstable solution, and you have to have expansion or contraction within standard cosmology. We know that in our case it's expansion, the galaxies recede from us, and also related to that and to the co-moving coordinates is the notion of the fundamental observers. So people, so the observers who sit on the co-moving coordinates are receding from each other according to this universal expansion. And of course, like standard plots of how this depends on some density parameters is shown here. I will not go in detail through that, but just worth remembering that we define things like density parameters in standard cosmology. Now, this expansion means that you have what we call Hubble-Lemaitre law in the local universe. First of all, one thing that you have in expanding models is that due to this recession, or actually it's just a property of the universe, let's say, the galaxies are redshifted from you, meaning that the light stretched out, the wavelength is stretched out, and you observe redshifts from emitted light from galaxies. A small distance of small redshifts, meaning much less than 1, you have this famous Hubble linear relation that actually Hubble tried to fit. If you look at his data, these are these red points here. And actually, he was really in the very local universe where there are large inhomogeneities, and he was like looking at, I think, Berg or something like that. And you don't really have the Hubble limit law there like that. So I don't think he really did a proper fit to his data. He was like guy by eye. But this one is from Hubble and Humason. Okay, there is unfortunately this. But so a bit later, which is much more solid, and there are other points which extend to farther than Hubble himself had. And this shows you already the linear Hubble limit law. Of course, you can generalize it to any redshift distance relation. There are equations for that. Remembering that distance is not well defined in cosmology, because again, here it is relativistic, that we don't really define a distance. We have to have some definitions like luminosity distance, angular diameter distance, etc. But we should work with space-time intervals. But there are relations for these distances as a function of redshift for any redshift. Redshift can be, so this is worth remembering that in cosmology redshift is not Doppler effect because it can be any value. CMB has a redshift of 1,000. Yes, so this is not the Doppler effect as in special relativity. And this is true for these fundamental observers, or in other words, observers in the Hubble flow, or those who would be static in convex coordinates. These are kind of equivalent. So that's why I'm talking about this will be clear in a moment. And this is because in real universe, we have inhomogeneities, and we have what we call peculiar motions, but I put them in quotation marks because they are not peculiar. I don't know why this name is. I'm not a historian, science historian, so I don't know, but they are called like that. In Polish, they are called swoiste, which is a bit better word, because it's like proper motions in astronomy is a different thing. Yeah? Proper motions are stellar motions. So they are called peculiar for galaxies. So universe is not locally homogeneous. And how we deal with it usually in theory and standard cosmology is that you separate out the background, which is the Friedman background, driven by this equation I showed, and you have local perturbations. Now, if you want to work out perturbation theory, of course, you work out this around the density contrast, which should be rather small, but you can still think of some higher order perturbation theory where these deltas are still large. And again, there are some problems with this that some people again say that this is not the proper way of dealing with this because you cannot have something like very large perturbations on top of a background because it's not formally correct, but this is how we usually do it. And what it then means that once you have these local inhomogeneities like galaxy clusters, you have gravitational pull, even if again in GR there is no gravity like a pull, but you can go be Newtonian here because the potentials are small and things like that. So here is an illustration of a paper where data are actually presented, and the colors are local density fields. So redder would be much over densities and bluer would be voids. And then the lines are flows, peculiar flows. So on top of the Hubble flow, which usually you can clearly see whenever people do such reconstructions that there are like outflows from voids and inflows towards clusters. Of course, voids don't have like a force that induce these outflows. This is like a result of the fact that you have inflows on what is between the voids. But in practice, this is what happens. And this is what we call peculiar velocities, this additional velocities on top of the Hubble flow. And formally, these are those velocities that you add up on the cosmological redshift. And here I use very simple linear approximation to make it simple, but you observe a redshift from a galaxy, and in practice, you really observe only the radial component of any motion of galaxies. There are a few galaxies where we can measure with some errors tangential velocities like Andromeda, maybe M33, Magellanic Clouds, that's it, I think, because they are so small that even instruments like Gaia or this kind cannot really measure them. So we really work with radial usually. So this bold here is not because there are vectors, it's just to highlight this. So we measure some redshift, but this redshift is composed of this cosmological one due to the Hubble flow and this peculiar velocity. Yeah? I used here, as I say, this approximation. So this is not proper addition of velocities, but first of all, these peculiarities are a big, well, significant component of the measured redshift only for very small redshifts. And secondly, these peculiarities are very, very small in terms of V over C. They are hardly ever above 10 to minus 3. You just don't have these kind of orbital motions in the universe. There is also, they still matter for higher redshifts because you observe what are called redshift space distortions at any redshift really. For redshift 1, you can also observe them, but they are then a statistical effect and not something that you can really measure with relation to the redshift that you measure on your spectrograph. Okay, so this previous relation could be reverted, and you can say that, okay, if I have a way to measure, I have z opsis on my spectrograph, it's very simple in that sense. If I have a way to measure R, and H naught is like a constant, it's another story, but whether we know it or not, but we know it's not 1, we know it's not 100, we know it's roughly 70 or something like that. But you can also change this in such a way that H naught would go out of these equations anyway, or you just fit to a monopole. The point is that you can try to measure the specular velocity of a galaxy if you have these two. So this comes from your spectrograph, and independently you have to have a way to measure R. And as any astronomer knows, measurements of distances are hard, not only for galaxies, but also for stars, for any objects. You can only send laser signals maybe to planets in the solar system, and that's the only direct measurement you can make. Then we can make measurements from parallaxes for stars, but for galaxies we can't. So this is a very hard topic. It's a whole topic of measuring distances of galaxies. There are many methods. There are some methods which are more independent, like from Cepheids, because the whole stuff about H naught is that you measure the distance relation. Yeah, so you have to measure the distances. You can then use some also secondary higher order relations for this. Just a quick summary, if you now look into the last DESI dark energy spectroscopic instrument release that has 10 to 8 redshifts already, spectroscopic redshift. So this part, Z ops, and then you compare to the best and largest peculiar velocity catalogs which have the distance estimates, you see that there are orders of magnitude differences because this is very difficult. Not to mention that measuring distance is getting harder and harder the farther you go because your systematics build up and you just start losing any constraining power. So this is the reality. There is a whole field of peculiar velocity cosmology and all that, but there is one peculiar velocity that we know, or we still think that we know very well. And whether we know it so well is another story. But I mentioned that there is a dipole component in the CMB. I think it's a very famous thing. It was measured already by the first Sirius satellite COBE, and it's a 10 to minus 3 amplitude, so 2 orders of magnitude more than the other components. And you can measure it then very, very well from your CMB because it's a dipole in the temperature. If you interpret it as a Doppler effect, you get this heliocentric velocity because all our satellites are in the solar system. Even if you send them to Lagrange point, they are still in the solar system. And there is a well-defined velocity, well-defined direction. I don't give errors here, but they are, I think, sub% from CMB alone. Fitting the dipole is very good. Now, heliocentric means that there is also motion of the sun. So if we want to really learn about what, I don't know, some kind of system in which we are in moves, you have to first reduce it to the galaxy center, and we know quite well the motion of the sun in the galaxy. But the problem is then the next step that our galaxy is not a fundamental observer because we fall on Andromeda. It's believed that we probably are on radial motion with maybe small tangential component, but there is something like barycenter of the local group. And reducing this is the main problem because we don't know it very well. We don't know the masses of Andromeda and our galaxy so well, in fact. So it's very hard. So that's, well, still people manage to do it, and there are some errors which are few % from that. And this gives you this velocity, which is a bit larger, like 600 kilometers per second. Still, what I mentioned is still less than V over C is less than 10 to minus 3. It would be on the larger side if you compare with the peculiar velocity catalogs. Usually the RMS is like 300, but okay, this is not such huge velocity. It's still the best constrained peculiar velocity of any galaxy, except for, of course, the radial motion of Andromeda, but then we don't know what falls on what. So, and as I mentioned, this we have mostly this barycenter uncertainty. But okay, this was just. We'll come back to measuring the heliocentric velocity. Ellis Baldwin in 1984 showed in a very short, nice paper that I invite you to read, that if we have such a peculiar motion, and we have some distribution of far away, so redshift 1, let's say, objects which are isotropically distributed, and they propose radio, and this was a very smart thing, you will see why, radio sources, you should have this imprinted in this, because you have actually not even general, but special relativistic effects of Doppler boosting and aberration. You basically, like in, I think it was in Star Wars, yeah, when they turned on warp, you see that things go like that, and it's exactly that effect, more or less. So you have two things that, first of all, the number counts kind of converge towards your motion, and also the fluxes, also the spectral index changes. And I have a derivation on the slide that I can show later, copied from the paper, but here I just give the equations. If you have some sources which have a power law flux of this form, if the number counts are of some power law, and then you have power law spectrum. So these two assumptions, which are very well met for radio, especially the second one is very well met for radio sources usually. Then you will get the amplitude, which is expressed this way. So this is our this heliocentric velocity again, and these are these terms x and alpha, which appear here. And we typically know that alpha should be around 0.75, x is around 1, so you get something like 4.610 to minus 3. The details depend on the catalog, etc. I will show this as well, but this is roughly what you get. And this is worth remembering that this dipole from radio sources should be around a few times 10 to minus 3. Also they showed, it was really a pioneer paper when radio data were very sparse, that you need at least 10 to 5 radio sources over the full sky for a detection of this effect, because you need to measure it, you need statistical power. So people have been trying. The first attempt was made over 25 years ago, because there were just not good enough data before that. People used NVSS. It was the famous full sky that you can see from the north radio catalog, and Blake and Wall published in Nature. And here I always tell this joke that we know in astronomy that if something is published in Nature, then it means it's wrong. In astronomy, it's very common. It's not like in medical sciences. But typically, and maybe this joke is quite appropriate here because nobody reproduced their measurements. They found very nicely matching dipole with what you expect, and the story was over for many years. However, when people started revisiting this, actually with the same data, but with some Nature paper doesn't have any details. You don't even know how they did it. But when you have like a paper that has details, nobody managed to reproduce it. People get some discrepant results, but they never find anything which would be of this order. They sometimes find much larger, sometimes many degrees away, and things like that. So this was a problem that kind of sparked a new interest in this with new data, and many surveys were used. The problem is that the one that I mentioned, that in fact we don't have a full sky radio catalog because we haven't yet built instruments, two identical instruments in two hemispheres, and this is not feasible. If you think even of LOFA or something like that, building a mirror instrument in the south is just not possible. It's so costly. So we don't really have a full sky radio catalog from one kind of type of observatory. So you always deal with partial sky, but still you can see, let's say, 3/4 of the sky from a given position on Earth. So there were atoms in different surveys and different frequencies. So just for those of you who are not experts in radio, you don't use really wavelengths, but you prefer frequencies, and you observe at specific frequencies because you have to tune your instrument for that. So you have to choose its frequency range. You cannot just measure any frequency because you need different detectors. Most of these results point to dipoles much larger than CMB value, but often in the CMB direction, which is the most puzzling thing. And here is one example from a previous paper where there is a measurement from NVSS that they did from RAX. So this is another survey from the south. Then this one is joined. So they try to merge these two into one catalog. And this is the dipole direction from CMB that you expect. So spot on. And then these are the amplitudes from many different surveys. So previous papers and this one, this is what you expect, and this is what you get within 3 sigma uncertainties. Again, a note for those non-astronomers. In astronomy, you often use 1 sigma because we want to show very small error bars. So we are happy we use 1 sigma. But here they are 3 sigma. So these are really many sigma away from, even if you had some, underestimated error bar, this is many sigma away from what you expect, and from many different surveys and different papers. So this is basically a consistent result. Some considerations to remember, that's what I mentioned already. You never have full sky. Secondly, our galaxy is bright in radio because there is synchrotron emission from many sources, so you have to mask it out. So you cut out even more of the sky. So you need an estimator to measure a dipole from such data. And people work on that. There is a whole literature on that. So this is quite well handled, I would say. This power flux, low flux dependence, and spectral index depend on frequencies. And so, for instance, here is a list of these are different frequencies. So these are large frequencies. These are smaller frequencies. You see that this X and this alpha are dependent on your survey. And X is usually very well constrained. Alpha is less constrained because to measure alpha, you need measurements in 2 frequencies at least, yeah, because you need to measure the power law. And then hardly any instrument gives you 2 frequencies. Usually you have to match with some other instruments, and that brings you significant errors or uncertainties on this. But still, it is quite well handled. And there are methods how to deal with this. Again, there was this Wagenfeld paper or some other papers, how to include this in your estimator. The bottom line is that whatever you take here from the data, you usually end up with 0.4, 0.85, 10 to minus 3. You never get more expected. So 0.4, 10 to minus 2.
Can you say again what is A and what is dx?
So A is the A. So this is alpha actually. So this is this.
Slope.
Slope of the frequency power law, because in radio this is synchrotron emission, so this is not thermal, so you have a power law. And dx is the expected value of this Ellis Baldwin dipole from this particular data. If you have this x, which is the slope of the counts that you measure, because counts rise usually as a power law, and then this is the index of the flux, so flux spectral index. This is the expected values of this Ellis Baldwin dipole.
So this is the amplitude?
Amplitude of the dipole in the maximum in the opposite directions, because there is a cosine term, but this is in the function directions of the motion.
The axis of the dipole, is it always, because it looked like, my understanding was the axis was off, right?
The expected axis in exactly in your CMB motion in the same.
It coincides. The expected one.
Yes, the measurements, well, this is just an example. The measurements, well, sometimes they are a bit off. So there is one measurement here that is here. So it's a few degrees off, or maybe more than few degrees. So they are not everybody gets them totally in line with the CMB dipole, but the expectation is that they should match.
So the thing is that the direction is usually not very far away, but the magnitude is very different.
The direction, the problem also is that if you don't have full sky, you have problems with measuring the dipole term. And there are systematics which can be large scale, and I will talk about this very shortly. But the consensus is that, there are not many measurements where the direction that you measure is very off from the CMB dipole. So the consensus is that and this is the problem, the puzzle, let's say, that the direction is usually in line with what you expect, or not very far. But yes, it's hard to it's quite hard to measure, especially in one of the coordinates I will show a table about that. So now coming to our recent contribution, which is this Böhme et al. Paper. Now I mentioned that you want to measure the boost and aberration number counts, but you can imagine that these number counts are not measured to infinite precision. You have many effects like shot noise, like instrumental effects and things like that, and you have to do it in a smart way. Usually what people do is that they, well, as we call it, pixelize the sky. So they decompose the sky into equal sized pixels, which is the same way as you do it with CMB. And you try to measure the counts per pixel to have at least the same area. And you have to model these counts somehow in your you have to build an estimator. And typically what you do with such measurements is that you have some point process, which gives you Poisson distribution for the expected counts. But in radio, it's not so simple. It was shown actually in previous paper that you expect rather something like negative binomial. And this is because radio data is tricky. Radio galaxies have weird morphologies. Often you have a central source and lobes because you have outflows. And what then happens that in your catalog, you will have, for instance, 3 sources next to each other, which are actually the same galaxy. Because you have sometimes even the central source is also not visible at all. You just have the lobes. If you don't include this into your estimator, you will have some over-dispersed, that's why with this name of the paper, the title of the paper, you have the over-dispersed counts. And in this paper, we mostly looked at how important this is for the dipole. Spoiler is that it's not very much.
What about strongly lensed? Did you artificially remove strongly lensed sources?
Well, the estimates are that this is a very, very small fraction, but no, we don't include this. The strong lens sources can be there, but from what I understand in radio, especially, you expect that the fraction is very, very small. But maybe
statistically, it should not bias.
Yeah, they should be also randomly distributed on the sky.
Yeah.
Because strong lensing is an effect of the deflector has to be already far away.
But if there's so few of them, then maybe the bias.
Yeah, maybe this is worth revisiting. Maybe somebody looked at it. I don't know. But here I don't think we worry about this at all. Anyway, the bottom line is that even with this better estimator, we don't find dipole consistent with CMB. But what we also did in this paper was we tried to apply this estimator to all the past data sets and consistently measure and also check where there are important systematics in these different surveys. And what we found is that there are some surveys which are, let's say, better for this, and some are worse because some have pretty severe systematics. For instance, there is a survey TGSS, which is in low frequencies done with an interferometer in India. It presents some systematics. I already knew it previously because I had a summer student a few years back where we looked at some correlations in this, and we already saw back then that this is really problematic. So there are some NVSS is maybe still the best. VLAS, which is a new survey with VLA, the same as NVSS, but it has systematics that you can see by eye that there are some inhomogeneous patterns in the distribution due to how the data are measured. It's another story, but it's a complicated thing in radio, very different from optical. Needless to say that you need to have some like wide angle correlation calibration for the sources because you cannot really measure flux in the same way as with optical, where you can night by night really measure how much flux you really get. So the point is that still, even if you take out this most problematic and you just join, for instance, southern hemisphere with a northern hemisphere survey, and here's you also at LOFAR, which is a very deep survey. With these, we still find something like 3.6 10 to minus 2, so almost 10 times or a few times more than you expect. Yes. So the directions vary, and you can see that there are some surveys where direction is not very well constrained. So we did 2 experiments here. That one is that you try to measure the direction and you try to measure the amplitude. So you have like 3 degrees of freedom, but you can also do that you assume that you measure the dipole in the direction of the CMB and what amplitude you get. So there are these 2 things. They are quite consistent. Here, this is like a free direction as well. So the uncertainties of a few degrees, these are not exactly the same direction, but not very far away. And the bottom line is that you, even with the most sophisticated at this point methods, you still get this this discrepancy. But that's not the end of the story. Even if I should soon finish, is that people are trying to compare these radio estimators with some other. So people are trying to think what kind of other sources could be used for the same type of test. So you need power law number counts and you need power law spectrum. If you think of galaxies in the optical, this is not the best, because in the optical you have very complicated spectrum, which is thermal. You have lines and you have many things. However, there are claims. I don't know. I haven't read in detail that paper, so I cannot comment so well. I am a bit skeptical, but there are claims that you can, if you take mid-infrared, it's emission due to heated dust. Maybe Böhme can comment if this makes sense. And that around at 4 micrometers, the quasars would be also a good type of source for that, because they have this power law emission there. That quasars are a good source in general. It's obvious because quasars are far away, and actually most of these radio sources are also usually AGNs or quasars. So quasars themselves, yes, they are good. Whether this wavelength is good, the alpha there is about 1, as they claim. And anyway, they use them. They have a quasar catalog. They constructed from a WISE satellite, and they measured in the more or less the same way. And they also find D, which is about 2 times 2R. So now, even if this measurement has some problems, because, for instance, I used WISE data a lot in my life, and I know they have severe systematics. Even if it was a special satellite, it had a very specific orbit, and it is very inhomogeneous coverage of the sky. But even if this is the case, even if there are systematics also in these measurements, why you should have from 2 different measurements from very different methods, all systematics that still give you the same kind of conclusion. This is something to think about. It doesn't, you can, of course, both can be wrong, but they are wrong in the same way, more or less. Yeah. So both the radio and the quasars from WISE find 2 large dipoles roughly consistent with the CMB direction. So this is a puzzle, but of course it will need to be revisited. We don't have any new satellite as WISE, but better. I don't think there is anything planned actually, because satellites James Webb just measure very small portions of the sky. There is nothing.
No chance for this kind of statistics.
So this is hard to test. Anyway, just as a maybe final slide is that there are other ways when we try to measure the specular velocity of the local group, or our galaxy, but the local group. Actually, I devoted my PhD thesis to something related. That's why I'm also interested in these dipoles. Is that in the standard approach, you can show that it's in Peebles, actually, I think 1980 already, that there is not only like a peculiar motion. Well, this peculiar motion has a velocity component, but you can also think of something like peculiar acceleration. So the acceleration in Newtonian sense induced by local inhomogeneities, and you can try to measure this by local galaxy distribution. You can try to basically look for a dipole term inducing this peculiar acceleration, and for many years, for the surveys that were used, the direction and this velocity is consistent with CMB. However, the problem is that this measurement is dependent on so-called galaxy bias factor, which is roughly 1, but not exactly. So it's not as pure measurement as this by Ellis and Baldwin, the proposed one. There are also some other ways when you reconstruct this whole peculiar velocity field around you. You can, within the reconstruction model, you also have your position. So then you can try to see how you are moving with respect to this reconstructed peculiar velocity field. And again, there are systematics, there are many problems, but practically none of these reconstructions points to our motion of much larger than 1,000 kilometers per second. which is what you would need to really be in line with the dipole that we find from galaxies, from radio galaxies. There are also some other, there was actually a proposal to look for some effect in optical galaxies, so in different way related to operation, but you have to make some other assumptions because of not power law character of these. They tried to apply this to SDSS, no measurement back then, but who knows, maybe with LSST or Euclid we can revisit this. So this is the summary. So this measurement from radio sources is puzzling in a sense that it's a simple test with well understood astrophysics, I would believe. There was nobody really who would be put into doubt the assumptions that are made. The power law count, because this is just what you observe, and the power law, the spectrum of these objects. Now, this gives roughly consistent direction with what you expect, but practically all the measurements, especially those which did it really thoroughly and with some well devised estimators, really give you amplitudes a few times too large. So from what we know about the local cosmography, so to say, this cannot be our local velocity of larger than 1,000 kilometers per second. First of all, because you would see this in the CMB dipole, yes? It's like this is the main inconsistency here, yeah? Because if we really were moving very fast, you would see in the CMB dipole, unless there is a very weird conspiracy from nature that CMB dipole has the Doppler effect component and some other inhomogeneity large scale, really large scales, which is exactly in the same direction, well, or maybe very close, and adds up to this Doppler effect, which would be very ironic from the nature, I think, and Einstein would be then wrong saying that nature is not mean to us. I don't think there is evidence for that, especially I think there would be some imprint of this also in higher order in CMB, from what I understand. If you had some kind of model where you have dipole term, well, you cannot have exactly, I think, perfectly dipole term in the distribution of the objects, I think. I don't know. Anyway, we don't know. And the only thing that you can think of is then between the CMB and today, there was a large scale anisotropy, which would be again a very weird cosmological model that in the early universe you don't have this, in the late you don't really have it. But then in the mean, like a redshift of 1, you have something very weird. So of course, systematics are there, but I forgot to say that all the analysis that people did, they did not point to any single systematic that could really give this very large amplitude. There are some small things that you have to take into account, like this proper estimate, or like the power law, like the inhomogeneity in your survey data. If you are careful, so just to mention here very quickly, if I go back to this, that when you do this, you always put some minimum flux on this. So you take a catalog of the radio galaxies and you say, I only include those which are above some minimum flux. And this minimum flux always is taken as many times larger than the minimum that the instrument can measure. To be in many sigma regime, that basically your uncertainties on the flux are very small. So people are very careful about that. So there is very hard to imagine a dipole type systematics that would be still there preserved. But at least nobody found them. And there will be final raw data at some point covering the whole northern sky. EMU is the southern sky radio experiment that is ongoing, which will cover the whole southern sky, so 3 pi radians basically, and SKA then, which will give many more sources, so much better statistics, and hopefully also less systematics, because people learn how to work with radio data over the years. So there is a hope that in the coming years we will have better measurements. But whether we will have the answer, I don't know. But the measurements should be better. So that's it. Thanks.
Okay. You have a question? Yes, I have a question as well. Sorry for that, because I actually asked you, Maciej, but you didn't answer. I'm very bad astronomer, so from the position of this dipole, I could not localize its direction on the sky. So I asked ChatGPT, and ChatGPT told me that this direction is perpendicular to the galaxy plane. if it is perpendicular to the galaxy plane, that I can bet quite a high amount of money that galaxy subtraction is the problem.
Yes, so the first of all, the CMB dipole is not pointing towards the specific structure in the universe. Yeah?
Well, but you have. Can you draw this picture? We have a galaxy plane. We are, of course, at the periphery of the galaxy, and where this dipole in 3D is pointing.
I have one. Okay, so LNB somewhere here. Well, I don't. Yeah, so you see this 260 and 15 heliocentric coordinates. Yeah, so well, I don't need to go.
So it's not perpendicular.
Well, that would be so. Okay, so we measure this way. So this would be
I'm not an astronomer by
this would be-
education,
this is,
sorry.
Somewhat yes. We measure the. This is 180. 0. Yeah, so that would be somewhat. Yeah. It's actually close to the
means-
so-called supergalactic plane, if you know what it is. It's a structure of galaxies around us.
No, but for the galaxy itself, it's not perpendicular because we are. I do not think about the sky. I always think about our location, right? And we have the galaxy, those spiral arms, whatever, and we are sitting something here. And this would be for me the direction perpendicular to the galaxy plane. And
Yeah,
this
so-
is my question: is it a right angle?
Well, it's not.
here
It's
or
not towards the pole. Yeah, it's 50 degrees, so it's not.
Yes, in the galactic coordinates, B is equal to 48, which is kind of more like 45 degrees with respect to.
Because you know here, of course, if you
Oh,
have any contamination, even
Yeah,
in radio from the galaxy, it
Yes,
might be
yes.
more important
That's
than
a- so,
anything
okay.
else.
So regarding the measurements of the radio dipole itself, yes, well, this is an array deck, so it's not the same, but there is, of course, this problem of subtracting the galaxy. I agree. But then I would expect that you should see something either in the galactic plane or indeed orthogonal. Yeah? I don't think we see this in any measurement. So if you
Because this
I have a-
effect is stronger in all those
Typically-
directions, right? So here you would have more problems, right? Here you see less problems with because we are not also localized. We are not at the symmetry axis.
Well, so this is the only map that I have unfortunately discovered partly, but in the equatorial coordinates, this is typically how your sky survey would look like that you want to use later for your measurements. I mean, I think there is also some hotspot here that is usually also marked out. But you will have this coverage of your survey, which is more than half of the sky usually, and then there is this the galaxy that you cut out. And in one of the papers, people played with larger, smaller cutouts. You can really be so aggressive with these cutouts that you have like B of plus minus 30 or 40, where you don't really expect any emission from the galaxy anymore, and you still, of course, the error bars then get larger because you have less of the sky, but I don't think there is evidence that galaxy would be driving this. But it's not excluded totally. Yes, that's true. And that's nothing we can do about, unfortunately, because that's what it is. In the radio, the galaxy is bright and you have to. But you know that CMB also has a galaxy in it. And these beautiful maps that you see are a bit cheating because the galaxy is taken out. And if you look into Planck data, you have full sky isotropic, well, anisotropic distribution. But this is not really what you measure. There are ways of painting. Well, you measure it different frequencies, so you are able to build a model and remove it. But in radio, it's more complicated. We don't have a model that we can remove from the measurements, so we just have to mask out. But yes, that's a possible systematic, but okay, that would be a systematic certainly inducing the direction, but would it affect the amplitude? This is the question, yeah? Because as I say, even if you mask more aggressively, you still find more or less the same results. So,
Okay, there are other questions. Mikołaj.
Okay. You mentioned the one possibility of explanation as a kind of large scale flow of matter for large Z. An obvious way to detect it would be to beam the data or to cut the data into various redshifts and see what happens in this case.
yes.
Of
Yes.
course, you lose the
The
number.
problem is that you cannot do it with radio data.
Even when you
the radio, yes, so just let me explain. So the radio data I'm talking about, that's what I forgot to say, are so-called continuum data, where you just measure the flux. In radio, unfortunately, due to non-thermal emission, the flux is not correlated with the distance. For optical galaxies, even your optical magnitude is a good indicator of distance that Hubble already used, because you have a redshift which redshifts the whole spectrum. In radio, the only thing well, the redshift will affect, of course, but you cannot estimate even the redshift from the radio continuum data. So the problem with these radio objects is that we know more or less where they are because we have both some specific measurements and also some expectations. We know they are at high redshift, but we cannot tell, and we cannot do tomography. We cannot tell at what redshift each individual object is. This is the main challenge with radio surveys also in general for cosmology, and Szymon here is an expert on that because he has been working on that in LOFAR. When we measure things like power spectra, correlation functions, we don't know the redshift distribution even of these things very well. We know more or less we can try to constrain. So yeah, so it's not possible. The only option would be to do the line radio measurement, so-called. You can do this in H1. You then measure something like spectroscopy. This is possible. And one of the SKE instruments is doing this. You measure, so basically you just measure, so you measure the 21 centimeter line of hydrogen, and you just measure a bit higher and larger and larger wavelength, so we can do tomography. Yes, this way, because you measure the redshift at 21 centimeter. The problem with this is that this is very, very weak signal, and then you can in practice do it up to redshift maybe 0.1, 0.2, because outside of that your signal is too low. And even SKA will not probably probe beyond, not certainly to redshifts of 1. You can do some pointed measurements, and so 21 centimeter times 2, basically. So
For all sources in a massive
then you have
way.
to observe for a very long time in a given place, but doing a full sky like that is not feasible with our even square kilometer array, unfortunately. So you would need some other sources. So as I say, maybe some future measurements at other wavelengths, maybe. Or yeah, I mean, okay. It's not exactly true what I'm saying in a sense that we try to match optical data with radio data, like LOFAR does. If you have very good resolution in the radio, you can quite unambiguously match some optical data, and you can try to learn about the redshifts of your objects, and maybe with LSST or Euclid, maybe together with the others, with radio surveys, this will be doable. Because also in radio, we now go to very small resolution thanks to large interferometers. So maybe one day we'll be able to do this tomography, but not yet. This is not possible.
Okay. Other questions? Amit?
So these dipole moments are measured based on mostly radio loud sources. Now, if we want to apply on quasars, so which are mostly radio quiet sources, then should we expect more systematic offset in the amplitude?
But then you have to do it in this infrared, right? And in the infrared, you have actually a bump and not quite power low, but still.
The amplitude in this what you expect is very simple. It just depends on that. Whatever, this is just example of radio sources, but if you had any other sources that would have meet these two, this is usually met also for optical galaxies, because you have if you measure number counts of optical galaxies, you have power law, 0.6 usually, that is so. But then this problem is this, the power law spectrum, But if you have such sources, in whatever type they are, this would be the expectation. You just have to plug in your X and alpha and you will get this. Now, Actually, the thing about these quasars, which are measured in mid-infrared, is that if this was correct, that they had these power laws, then they would be actually a very nice thing to use, because the systematics would be very different. The amplitude would be just based on the x and alpha that you have, but your measurement, the systematics of the measurement should be very different from the radio sources. And this was one of the arguments that people use why this is like a useful measurement and why this is even more puzzling. But I know that these are very different sources than in the radio catalogs, in the sense that in radio you have, well, mostly AGNs, but also star-forming galaxies. Yeah, so anything that has synchrotron emission. And in quasars, yeah, so that they are very different selection. But the amplitude in this test just depends on this assumption. There is nothing about, of course, again, if you go in details to the papers that I have on the slides, if you have not full sky, if you have a mask, then there are some details of that, because you have to like a model, an estimator of the dipole component, because this one is just the dipole, which is, in fact, you have the full sky distribution, which I can just show here, because there is a cosine term. Yeah? So in fact, this is your like distribution of your number counts over the sky. Yeah? So this is, there is a, it's not, dipole is just in the direction of the dipole, but okay, this is not.
Other questions?
So when you showed your numbers, they were different for different instruments, right?
Yes.
So so the velocity is really how fast we are moving with respect to something which would have been homogeneous. That's the point.
Yes, the test gives you what dipole term you should have if your measurement measures this relative.
But this D measures the velocity essentially. That's
yes. I mean, this should be translated then. So because this is in the dipole amplitude. So for 370, the amplitude is 0.40. 0.45 in this term. So that would be like a velocity of 8 times 4. So, well, up to even 2000 or something like that. So 3.6 times, yeah, 8 times 370. So this is the velocity that you would, if this was really a measurement of your motion, as this test should give you, that would be the maximum velocity. So in the dipole direction, that would be this velocity.
So depending upon the instrument, you find different velocities from this table. Is it what you're saying?
Yes, in essence, yes.
CMB gives to something else.
Indeed. You have different instruments give you different dipole amplitude, meaning that.
But the direction is more or less the same. But
yeah, well, okay, you have to compare this really, because otherwise it's not time. So, well, I mean.
But
you have to measure the how many degrees away this is, but it's not far off. It's not that like orthogonal or something like that. It's more or less around the single dipole.
But these each instrument uses same frequencies or different frequencies?
No. These are very different. So I don't have a list, but this is I think gigahertz, and this is. Also gigahertz, and this is some. Oh no, sorry, there are frequencies, 3000 megahertz, and so these are different frequencies, wide range. But in radio, we expect that this is still the same emission. I mean, this is all this synchrotron. You just probe different part of the flux. It's the same mechanism, more or less, I believe.
But so if you look at the first two instruments, they would have the same frequency but completely different numbers.
Yes, and actually those two are not very good for this measurement, because log DR2 covers a very small portion of the sky. It's not even here, but it's much less than half of the sky. And TGSS covers a lot of the sky, but we know there are severe systematics in the data.
So the error bars are not trustworthy, that's what you're saying.
Yeah, so these are error bars after you include the systematics that you know, but certainly they are not fully systematic. And in particular, we don't really trust this very, very high value here. So the dose which we kind of find fiducial are these two, which are the best known in terms of systematics. So RAX, which is a southern instrument, well, measurements from a southern instrument, and NDSS. So, which doesn't mean they have no systematics, but these are the best. The systematics are most under control, I would say, in this instrument.
Oh, there was a question over there. Yes.
Yeah, I
go
just
ahead.
wondered how much with these different surveys, how much overlap there was between them in terms of did they have the same sources inside? 'Cause
Yeah, there is a lot of overlap. Some of them are actually covering the whole, so the same part of the sky. So PGSS, NVSS, and GLASS will be the whole south, the same northern sky. RAGs are actually two different frequencies from the same instrument. So the combination here is basically that you first of all remove those which are common, and then you have to choose because they usually overlap. So even if you have southern and northern instrument, then they see the whole sky from their viewpoint. So there is overlap on the equator, larger or less. So first of all, you have to choose where you cut. So you usually cut one of the catalogs. You try to preserve as much as you can from the more trustworthy catalog, first of all, and then you remove duplicates, and that you do well, usually in some probabilistic manner because the resolution is a few arc seconds, so you never know whether the sources which are within less than that are exactly the same source. Or people have methods of doing this when they combine different instruments or even compare with optical data. You have to build some probabilistic matching algorithm because it's again it's very different from optical astronomy when you measure like Gaia gives you sub-arc second resolution and you know exactly that this is the same source in some other catalog. In radio, it's not that simple, but I don't think this would drive you any problems anyway because as you see these measurements. Well, even if there are large error bars, but roughly you get well. Actually, if you combine, okay, these are maybe larger than if you take separate surveys. But in some other papers, people, I think there was one of these earlier. Yeah, so here there was a different way of combining this, and also you were getting. NDSS plus RAGs, but separately NDSS and RAGs still give you amplitudes which are large. So this is not the driving factor here.
I understand we have to live with the puzzle for the next year.
Yeah, so some people comment that it's really weird that it's not making like first pages because it's as severe in terms of sigma as the Hubble. But maybe the reason is that there is no dipole, no Nobel Prize winner involved in this analysis, so that's why you don't hear about this. But yeah, it's yeah. I think there is still a lot to extract from radio data.
I think we should be finishing
Okay.
because we have to see the room. So let's thank Maciej for